All right, now let's go back to the calculation of SEE just so we can see that real quick. We'll get another look at this, by the way, in the next reading. So what this allows us to do, once we have the ANOVA table put together, is to calculate the goodness of fit measure. So the SSE is equal to the square root of the MSE. All right. So what do you need to know for this? Well, one, you need to know how to calculate the MSE out of the ANOVA table. Okay, realize that this is a measure of goodness of fit, and all we can really do with this within the curriculum is to remember that the lower the SEE, the better. All right? Okay, and now talking about our second thing, so as we said, we can use this ANOVA table for three things. We're going to see two of them in this reading. So we can also come up with an R square. So an R square is also a measure of goodness of fit, and probably the most common measure of goodness of fit. And this measures the percent of the total variation in the dependent variable that's explained by the x variable. So if we get an R square equal to 0.25, what that says is, so if we're regressing housing starts against interest rates, what that says is variation in interest rates explains 25% of the variation in housing starts. So this is obviously going to be bounded by 0 below and by 1 above. You can't explain less than 0% of the variability, and you can't explain more than 100% of the variability. So you can't conclude causation, okay, because of this idea of and you have to be careful of this idea of spurious correlation also. So what does all this mean? Okay, well, I guess we ought to tell you why this is coming up with ANOVA first. Okay, well, how do you calculate R squared? Well, SST is the total variability, okay, and RSS is what is explained by the simple linear regression, right? So all we're saying is, well, if there were, let's say SST was equal to 100, okay, and the RSS was equal to 75, what that's saying is we explain 75 out of 100 for the sum of squares. That is, we are explaining 75% of the variation. Now, for simple linear regression, and for simple linear regression only, the R square is the correlation coefficient squared between the x and y. So if we took the correlation coefficient and we squared it, okay, then we would get the R square. Maybe a useful fact, but that's only good for simple linear regression. It won't apply in the next reading. So looking, well, let's see, make sure I know where I'm at. Okay, so here what we see is because the dots are a long way from the line, well, we estimated a slope coefficient, but that sure didn't tell us much about this data because there's so much error over here, right? So this would be a low R square and a high SEE. On the other hand, this regression equation tells us a lot, right? Because now we have a high R square. We understand this data set very well because the dots are all very close to the line. High R square, low SEE. Both of these are called measures of goodness of fit, R square and SEE. Okay, so looking at how we would calculate this, it's kind of a review here. R square is going to be the regression sum of squares divided by SST, so we see that over here. So 17.3 over 23 tells us we're explaining 75.2% of the total variability, and the SEE is just the square root of the MSE, so we get 0.775. This number is a lot harder to interpret independently. It's not bounded by 0 and 1 or anything. All you can really remember there is that low is better. All right? And to kind of wrap things up here in terms of the limitations of regression, remember that we're going to have issues with this because, one, the relationships change over time. We call that parameter instability. So we estimate a regression equation in one period, and it's going to we try to rely on those estimates in the next period, and things have changed. This is difficult to apply because of specification issues that we're going to go into in some detail in the next reading. And all those assumptions we talked about, if those are violated, that's going to create serious problems. We're also going to talk about that in the next reading. And finally, and maybe most profound from an economic point of view, is that the usefulness of this might be limited for investment applications because all the market participants are looking at the same data and running the same regression. So remember, it's not enough to be good. You've got to be better than everyone else, right? You've got to be quicker and you've got to understand what's going on. So that's always going to be an issue. If everyone can see the relationships, then it's going to be hard for you to use it to your advantage. So what are going to be the keys to the exam here? Well, certainly, the idea of correlation, that's the foundational concept for portfolio theory. Regression analysis here. This was a great introduction to what's going on with regression. Don't forget about confidence intervals and especially t-tests. Okay? And then the ANOVA table is something that you may have to work with just a little bit. Okay? Now here's a maybe a strange piece of advice for you, and that is if you feel like you got this topic summary down, and you're thinking, maybe I ought to go back over that one more time. So you got it down, but you're a little shaky. My advice is that you don't. Why? Because almost everything that we've talked about here that is generally applicable will also be covered elsewhere in the curriculum, in particular in the next topic summary. So the next topic summary, where we move to multiple regression, will contain a more general set of results. So, so if you kind of got the basics down here, you understand correlation, you understand what regression is doing, know a little bit about the ANOVA table, understand the t-test, you're ready to move on, and that next reading is going to be a real workhorse in the discipline and likely a real workhorse for the exam. Now, let's move on into our multiple regression topic summary, and you can tell that this is going to be something that's going to require some relative effort just because of this idea down here at the bottom that it says, here's the topic review, part 1. That, of course, implies that there must be a part 2, so it's something we're not even going to be able to shoot in one clip. So it's going to take us a little while to get through this material. However, you'll notice two things. One, anything that we did that was particularly important out of the first reading in this study session is going to be repeated here. So we're going to essentially take what we learned for simple linear regression, and we're going to apply that and expand it to multiple regression. And two, that this is going to be the area that test questions are going to come out of. So we basically have three readings: simple linear regression, multiple regression, and then time series. Time series is its own world, and I think that is certainly possible that you could see an item set that comes out of time series, although I would personally expect that to be a lower probability bet just because this, that is multiple regression, is the workhorse of the discipline. So we're going to go through this. It's going to take a little time to get through it, but I think if you will focus on this reading first, so if you got the basic principles from simple linear regression, if you focus here, then one, that's going to get you some traction on the exam, and two, it's going to make the stuff we do in time series a little bit easier. So moving forward, here's what we're trying to do. So we're going to go in and we're going to say, well, now, instead of taking housing starts and explaining them as a function of interest rates, we're going to take housing starts and explain it as a function of interest rates and as a function of lumber prices and as a function of economic activity and however many other things we would want to put into our particular stew here. So all we're doing is estimating an equation that has a number of independent variables. There's no theoretical upper limit on the number of independent variables. There's some rules of thumb, like you need at least 10 observations for every independent variable, or 20 observations, depending on who you're talking to. But, I mean, this can be 2, and it can be 22, or it can be 102. Now, I've never seen one with 102, but nonetheless, there's no theoretical upper limit. We still have a single dependent variable, housing starts. Now we're trying to explain it in terms of a number of independent variables, so we're looking for the variation in the independent variables to explain the dependent variable. And while this gets, while it would become visually complex, so if we're doing simple linear regression, we can do that in a linear plane. Okay, if we add a second variable, that is, we're looking at interest rates and economic activity, then we would have to move into three-dimensional space in order to look at the straight line. Well, once we go to 3 independent variables, then we're going to be in multi-dimensional space or n-dimensional space, and that is, of course, hard to visualize. Nonetheless, the intuition that we achieved when we were talking about simple linear regression in the first reading in the study session, we simply said, look, we're trying to estimate a straight line. This is still a straight line, right? So there's no higher order terms here. We're just going to have a number of independent variables, that is x's. Each of these x's then is going to have a slope coefficient, and the slope coefficient is going to be the real item of interest in the output. So just like we tested the significance of a slope coefficient in the last reading, we can test the slope coefficients of the individual we can test the significance of the individual slope coefficients in this reading. Okay? And of course, we still have the epsilon here on the end, which is reminding us that we are estimating this relationship with error. All right, so what we're going to do is we're going to formulate an example so that we can use that to talk about the different aspects of multiple regression. And what we've done here is we've gone to an old issue of the Financial Analyst Journal from back in 2002, and there was a reading there, and here's the authors that tried to, or attempted to explain hedge fund returns, okay, and they did that with 3 indices. They did that with a small cap stock index, okay, they did it with a high yield bond index, and they did that with an emerging market index. So what we're trying to do is we're asking the question, are hedge fund returns explained by the variation in these 3 indices? So we're going to take hedge fund returns, okay, so they will have, on our spreadsheet, we'll have a column of hedge fund returns, okay, that's going to be monthly observations for a certain number of months. Then we're going to have a column of small cap returns from that index, the Wilshire index. We're going to have a column of returns for high yield bonds and a column of returns for emerging market. Of course, these are going to be time matched, so we're looking at April of 1999. That'll be all the way across, and we're going to regress, okay, the hedge fund returns against the other 3 variables. All right. So in this case, we're going to have 3 explanatory variables. So here's the equation that we're estimating. So we're going to say hedge fund returns are equal to an intercept plus beta 1 times this Wilshire index, plus beta 2 times the high yield bond index, plus beta 3 times this emerging market index, the IFC, and then we have the epsilon term on the end. So this is just the definition of the abbreviations in the equation. So hedge fund returns, the Wilshire, the high yield bond index, and the IFC emerging market index are going to be our data in this regression analysis. So when we actually go in and start looking at this, okay, we're going to have n is going to be 93, so that's going to be 93 observations. So this is monthly observations. We have the hedge fund index. We look at 93 monthly observations on return. We have exactly the same observations for our 3 independent variables. And here we're going to see k is equal to 3. N is always going to be sample size. K in this reading is always going to be the number of independent variables. So as we go through, you're going to see some examples later on, because we're going to go back to ANOVA and those types of things, and you're going to want to remember this. N is 93 and K is equal to 3. And the data actually runs January 94 through September 2001, but it could be any period, all right? So the N and K, you're going to see some variables described in terms of N and K, so you'll want to keep that in mind as we go through. All right, so interpreting p-values. Now, we talked about in the last reading a couple of ways to interpret the significance of a coefficient. So one way was to perform a hypothesis test. So we asked the question, is this coefficient significantly different from 0? So we took the coefficient, we subtracted off 0, we divided it by the standard error. That gave us a t-stat. We compared that to the critical t-stat, and that was, we could either reject the null hypothesis or we could fail to reject the null hypothesis. We also then looked at a confidence interval. And a confidence interval said, here, let's take our estimated random variable, that is our coefficient, and we're going to bracket that by a certain distance, and we're going to say, well, is 0 in that bracket? Okay, well, if 0 was not in the confidence interval, then we discussed that you could, in fact, reject the idea that that variable was equal to 0, since 0 wasn't in the confidence interval, at whatever confidence level was used to estimate the interval to begin with. So what we have here is essentially a third way of doing the same thing. So hypothesis test, confidence intervals, and now p-values. And p-values are very easy to use. They may be a little harder for some candidates to understand. But what this says is, what we want to do is we want to test whether or not this coefficient is significantly different from 0. So that's what we did with the hypothesis test. But rather than calculate a test statistic and compare it to the critical value, we're just going to ask, what is the smallest significance level, that is the smallest alpha, okay, or the highest confidence level, at which we would be able to reject H0. Okay, so we're using p-values to do hypothesis testing. If the p-value itself is less than alpha, so if we're at a 95% confidence level, we're using a 5% alpha, so 95 and 5 equals 100, right? 95% confidence level, 5% alpha. If the p-value is less than alpha, then we can reject H0. Okay, if the p-value is greater than alpha, then we fail to reject H0. So think of it like this. We're testing an environment where we need 95% confidence, okay, so we're using a 5% alpha. Okay, we actually calculate a p-value of 0.07, In that case, what that's saying is, literally what that's saying is if we were testing at the 93% confidence level, that is a 7% alpha, we would just be able to reject the null hypothesis. But here, when we specified the alpha as the researcher, we specified as alpha. Okay, we said we need 95% confidence on this test. Okay, what we get is something less than 95% because we only get a calculated p-value of 7%, which would imply a confidence level of 93%. So, given standard inference levels, we say we could not reject HO if we were using a 5% significance level. Okay, but if we moved up to a 10% significance level or a 90% confidence level, then we would be able to reject. So that's what you see down here with the second little bullet point. If you're looking at 90% confidence and you get an alpha of 0.07, well, 90% confidence means an alpha of 10% or 0.1. If the p-value is smaller than the alpha, then you can reject the idea that the coefficient is equal to 0. Now, that's a lot of talk for a fairly simple concept, and if that's confusing, you just remember this. What we want, okay, if we're looking for significant relationships, is we want big t-values, where big is going to be defined as something bigger than something that looks like 2-ish. Okay, we want big t-values, or we want small p-values, where small is less than 0.05. All right? So p-values and hypothesis test, confidence intervals, all looking at the same thing. All right, so going back to our data now. So we're looking at the regression output for our regression of hedge fund returns against the 3 independent variables. This is what we get from our statistical package. So this is the starting point for the statistical analysis that we would most frequently see on the exam. You're not actually going to be calculating the coefficients. It can be done in simple linear regression by hand. It just involves all sorts of summations and, lots of arithmetic. It's terrible. Anyway, so what we're going to be doing is interpreting the output of regression equations in all likelihood. So what we have is we've regressed hedge fund returns against the 3 independent variables. So we're going to get an intercept, and here are our 3 independent variables, okay, the small cap, the high yield bonds, and the emerging markets. And what we're given the coefficients themselves. So if we look at the emerging markets, the coefficient on the emerging market variable is 0.101. We're also given all of the standard errors. So then we can also calculate a t-statistic. So for the emerging market coefficient, we can take 0.101, we can divide it by 0.017, and we get a t-stat of 5.9. Well, if you get a t-stat of 5.9, do you need to actually go in and calculate the critical value? No, you're going to be way over 2 there. But notice the p-value. What's that telling us? Well, that tells us that we could reject the null hypothesis that this 0.101 is actually equal to 0, even if we were at the beyond the 99.9% confidence level. All right. So when we calculate a hypothesis test, or when we're looking at regression output, we're given very frequently the calculated t-values. All we have to do is interpret them. For testing purposes, notice here that they didn't give us the calculated t-value for the Wilshire index or the small cap index. Okay, but the way we would get that, of course, is we take the coefficient, subtract off the hypothesized value, which is very frequently 0. In fact, the t-stats given in the regression output assume that the hypothesized value is 0. But anyway, we take the coefficient, subtract off the hypothesized value, divide it by the standard error, and that would give us the t-stat here. Now, when we do that, and we're going to do it in just a moment, okay, what we're going to see is that the t-value the t-stat's going to come out to be bigger than 2, actually a lot bigger than 2. How do I know that? Well, of course, I know that you take 0.2 and divide it by 0.02. Well, you're going to get a number that's bigger than 2, of course. But I can also tell that by looking at the p-value. I got a really small p-value. So even if I were at the 99.9% confidence level, I would still be able to reject the idea that this 0.278 was equal to 0. All right? So that's the data we're going to be given, going in and looking at how we might use it. Remember when we were going through the simple linear regression reading, I told you, well, here's some formulas for calculating t-statistics, but you probably don't want to memorize those because you're going to see a more general version of that in the next topic area. Well, here we are at the next topic area. And the difference is, when we did this for simple linear regression, we said the t-statistic was distributed with n minus 2 degrees of freedom. Well, notice that's the same thing, right? Because in simple linear regression, by definition, k is equal to 1, so we get n minus 1 minus 1, that's n minus 2. So it's the same thing, but this is a little more robust definition, n minus k minus 1. So here, if we're going to look at the regression that we're doing, we had 93 observations. Okay, oops, that's supposed to be a 3. We had 3, k is equal to 3 independent variables, minus 1, so what we have here is 89 degrees of freedom. So to calculate or to look up the critical t-value, we're going to go across the top of the table to get to the level of significance that we're looking for, and we're going to go down to 89 degrees of freedom, and we're going to get some number that's getting very close to 2, since we have a lot of degrees of freedom. Once the degrees of freedom get over about 30, then everything starts to look like 1.96, essentially. All right, so this is the exact formula we saw in the last reading. Our test statistic is the estimated variable, b hat, minus the hypothesized value, which can be anything, divided by the standard error. Frequently what we're doing is testing statistical significance, where the hypothesized value is going to be 0, right? So it ends up being the hypothesized value minus 0, or just the hypothesized value. I didn't say it right. It ends up being the estimated value minus 0, okay? So just the estimated value divided by the standard error, and that is the t that we get in the table on the last slide. So we go back and look at the regression output. It gives us the t's, and we said it was 5.9 for the emerging markets index. Well, that's simply the coefficient divided by the standard error. All right, so and these are important, certainly something that you want to have on your formula sheet. So looking at the Wilshire Index, we could go in and test this now. So we want to test it. We already know the result because we looked at the p-value, but just to follow up, okay, we're going to test the statistical significance of the coefficient. Okay, that term, statistical significance, means that we are going to test the coefficient relative to 0, okay, at the 5% significance level or the 95% confidence level. So H0 is going to be that beta is equal to 1 versus the alternative that it's not equal to 1. We calculate the test statistic. We take the estimated coefficient minus 0, or the estimated coefficient 0.278, divided by the given standard error, and that gives us a t-stat of 12.6. Notice that that is way gone from 2. We look up the critical value in the table. It ends up being about 2. So we can reject the null hypothesis that this coefficient, 0.278, is actually equal to 0, and we can accept the alternative that it is equal to 0. And we can do that at 95%, but we could also do it at 99, and we could do it at 99.9 because the table tells us that the p-value is beyond 0.001, it says less than 0.001. So when we look at the picture here, what we would see is that we were looking for, we had a fail to reject region from 2 to, from 2 to minus 2. If the t-stat we calculated had been anywhere in that range, we wouldn't be able to conclude that we were statistically different from 0. If we're outside that range, we're in the tail. Of course, we are way up here, right, at 12. That's a huge t-stat. Okay, so the probability that this is actually equal to 0, okay, the truth is that this coefficient is equal to 0 when we observe this observation that it's 12.6 standard deviations above the hypothesized value. The odds there look pretty small. All right? Okay, so when interpreting the coefficients, okay, what if all of the independent variables are simultaneously equal to 0? Then hedge fund returns are predicted to be 0.008. Okay, that is the intercept. And when we're interpreting the coefficients, it's important to remember this all else constant interpretation. So a 1% increase in the Wilshire Index. Okay, so if the Wilshire Index goes up by 1%, what's going to happen to hedge fund returns? Well, it's going to be the change in the index times the coefficient of 0.278, so we're going to end up with a 0.278% increase in hedge fund returns. That's the typical relationship. We get a 1 unit increase in the Wilshire Index, we get a 0.278 increase in the hedge fund returns. What about for the emerging markets? Well, a 1% increase there leads to a 0.101% increase in hedge funds. What about the high yield bonds? Well, what we would say here is that high yield bonds are not influenced by, hedge fund returns are not influenced by high yield bonds. Why? Because the p-value told us that this variable was insignificant, right? So we get a p-value of 0.13, which is much greater than the confidence level we're using of 95%, which would lead us to an alpha of 5%. Now, if for some reason we said we only need to be, we can work at the 85% confidence or 85% confidence level, that would tell us that we had a 15% alpha. Okay, so the alpha here would be 0.15. That's supposed to be a percent sign on the end there. And so in this case, we would be able to say, yeah, we at the 85% confidence level, we would think that the high yield bonds were significant. But that's not what we're doing. We're doing this with a 95% confidence level. That's what I would expect to see on the exam, by the way. So in this case, we're going to say, given our confidence level, high-yield bonds are not or hedge fund returns are not influenced by high-yield bonds. Okay? All right, so moving ahead. So what about testing the IFC coefficient here? And so we're looking at this, and we want to test, in this case, whether it is greater than 8% at the 5% significance level. So what we're going to do, 0.08, so we're going to look at this and say, well, we calculated 0.101. We want to test and see if that is statistically different than 0.08. Now, haven't we already seen a t-test on this emerging market coefficient? We have, but remember, the t-test in the regression output assumes that we are comparing this to 0. Right? That's where if we did that, well, that's where we got the 5.9, right? So we know that we feel comfortable saying this is statistically different from 0, but now, for some reason, and we don't have to know why, we can make up any hypothesized value, we want to compare that coefficient to 0.08, so we take the estimated variable, subtract off the hypothesized value, divide by the standard error, we get a t-stat of 1.2. What does that tell me? Okay, we can't conclude with 95% confidence that this variable is significantly different than 0.08. Why? Because the critical value is 1.65, so this for a one-tailed test, of course, so we're not going to be able to reject the null hypothesis. So we fail to reject the null that the coefficient is different than 0.08, so that's what we do. We fail to reject the null, just like we talked about when we were reviewing hypothesis testing in the last reading. So anyway, that would be testing relative to something other than 0. Thought we ought to throw one of those in just to make sure that everyone understood that you can do that. What about confidence intervals? Remember, all the confidence intervals in the curriculum, let me make sure I didn't skip a slide there. Okay, we're good. Okay, so all the confidence intervals in the curriculum are going to be constructed the same way. That's going to be a point estimate plus and minus a quantity based on a reliability factor and a variability factor. So in this case, we're doing a confidence interval on the Wilshire index coefficient. So we're going to take the reliability factor, that is our t-stat. Our variability factor is going to be the standard error. So we're going to take 2 times 0.02. Okay, we're going to multiply that together. We're going to add that to 0.278. We're going to subtract it from 0.278, and we end up with our confidence interval here, 0.234 to 0.322. So we tested originally the idea of whether or not this coefficient was equal to 0. Okay, and of course, we're able to reject the idea that this coefficient is equal to 0 because 0 is not in the interval. But if I wanted to test whether or not this was equal to, say, 0.25, so if you want to test whether or not this coefficient is statistically different from 0.25 at the 95% level, you will not be able to reject the null hypothesis. Why? Because 0.25 is in the confidence interval. All right. So just like we've seen in all of our previous calculations of confidence intervals, like we're going to see in all future calculations of confidence intervals, it's going to be a point estimate plus and minus a quantity based on reliability, in this case a t-value, and variability, the standard error here. So anyway, and that gives us a confidence interval, and we can see now that we have 3 ways to test that. We can look at confidence intervals, we can look at p-values, or the most common is to simply do a t-test or a hypothesis test. What about predicted values? One little twist here to keep track of. Talked about predicted values when we were talking about simple linear regression. That says, hey, we have an estimated regression coefficient, an estimated regression equation, so we know all of our estimated coefficients. All we had to do was find the forecast value of the x variable and plug that into the equation. We're doing exactly the same thing here. So if they tell us that the Wilshire index is going to be 10%, we can plug that in. If the high yield index is going to be 3%, we can plug that in. And if the emerging market is going to be minus 2%, we plug that into our equation. Okay, we do the arithmetic, and we get a predicted value of 0.037. Okay, well, so the only thing here that might be confusing to you is you get on the exam and you start thinking, always dangerous. Okay, but anyway, remember we said that the high yield bond index is not statistically significant. So this coefficient, 0.112, is not statistically significant. So some people say, well, we'll just leave that out of our predicted value estimates. Okay, well, it is still a placeholder. Okay, so you could take that variable out and rerun your regression with 2 independent variables, that is the Wilshire and the emerging markets, and then use those coefficients. That would be another alternative. But given the coefficient that we've estimated, we will have to have an estimate for high yield bonds, and we will have to plug that into our predicted value. Okay, so don't start thinking that you leave insignificant coefficients out of your prediction of the y variable when we're dealing with regression equations. Okay, so, and of course the predicted values for all of the inputs would have to be given to us on the exam. All right, now what about assumptions of multiple regression? Okay, remember we saw an assumptions list in simple linear regression also, and I told you, hey, don't worry about memorizing that because we're going to see a better list in the next reading. Well, here we are in the next topic summary, and we have a better list. So we saw most of these when we were looking at in the previous list, in the previous reading. Okay, there is one new one, and that is that there's no exact linear relationship among the x's. Notice that we didn't have that when we only had one x, because if you only have one independent variable, you don't have to worry about the relationship among the independent variables. There's only one of them, right? But when you have more than one independent variable, then we have to worry about this linear relationship among those variables. And as it turns out, that's going to be one of the big three. So we're going to have three of these in particular that we're going to come back and investigate. Okay, we're going to talk about this idea of a relationship among the x variables. If that assumption is violated, we're going to have multicollinearity. We're going to talk about the variance of the error term. If that assumption is violated, we're going to have heteroscedasticity. Okay, and then we're going to talk about the error terms being serially correlated. And if that assumption is violated, then we're going to have this serial correlation, also called autocorrelation. And we're going to have to come back and investigate those three assumption violations very closely, so you'll see that as we get a little further into the reading. But I think that's actually a big deal here in this multiple regression reading in the quant method stuff. So you do have to memorize this list. Okay, if I were the emperor of the world, I wouldn't make you memorize lists for the CFA exam, but these questions do show up, so yes, unfortunately you do have to memorize it. And in case you're wondering, yes, life does suck. So anyway, all right, so looking at this, let's go in and talk about the F statistic. So here we're going to do another type of hypothesis test. Now this is sort of a weird one, okay, because we're going to be using an F distribution. Now we used an F distribution in one of the tests we did at level 1. So when we were testing the equivalence of two variances from independent samples at level 1, you may remember that we used an F test. Well, what we're looking at here is the F test. Okay? This is the most common F test that you're going to see in the CFA curriculum. It's by far the most common one that I've ever seen in my career. So anyway, so the F test, it has a couple of things to remember. One, it's distributed F. Okay, two, it is going to have a very weird null and alternative hypothesis structure. And also, when we were talking about ANOVA, I told you there's three things that you're going to use an ANOVA table for. So one of those was to calculate an R square. Okay, we're going to take that out of simple linear regression, and we're going to plant it here just like we learned it. We can calculate the SEE, the standard error of the estimate, via the ANOVA table. We talked about that. We're going to plant it right here. So those two we've already covered. The F test is going to be the third thing that we can do with the ANOVA table. So for the ANOVA table, which we'll get to in a minute, we're going to talk about, here's the ANOVA table, let's finish it out, and then what are we going to do with it? Well, we're going to be able to go in and calculate three things: R squared, the SEE, and what we're talking about here, the F test. Now, what about this hypothesis structure? And so the hypothesis structure, this is a little bit strange. The null hypothesis is that all the slope coefficients are simultaneously equal to 0, versus the alternative that at least one of the slope coefficients is not equal to 0. Okay? The terminology or the wording that you may see on the exam is that you're testing the significance of the model. So you're testing the significance of the model when you're doing an F test. So think about this. We talked about hypothesis tests for the individual coefficients, so we can test the individual coefficients one at a time. Now we can test all the coefficients together with the F test. So if we in the null hypothesis, all the slope coefficients are simultaneously equal to 0. If we reject that and accept the alternative, then what we would say is that it appears that the model is significant, right? So if we reject HO, the F statistic exceeds the critical value. Okay, the shape of the F distribution is determined by two separate degrees of freedom, a numerator degrees of freedom and a denominator degrees of freedom. The F is also an asymmetric distribution, so it looks something like this within the very limited artistic abilities that I possess. Okay, we're going to have a critical F here. Okay, that's something we're going to look up. And what this is saying down here, that we have 2 degrees of freedom, we have to have 2 degrees of freedom to look up the critical value. Now that's okay, because if you know the ANOVA table, it's going to be easy to remember them. But basically, the F distribution is going to be calculated as one number over another number. There's going to be a degrees of freedom associated with the numerator, a degrees of freedom associated with the denominator, and you're going to go to the F table, which I'll show an example of in a minute. You're going to go to the F table, and you're going to look up the critical F. If you are greater than this critical F, that is, you're out here, okay, well, this is going to be the area where you're going to reject the null hypothesis that all the coefficients are simultaneously equal to 0 and accept the alternative that at least one of the coefficients is different from 0. All right? So testing the significance of the model. So here's how we would calculate this. We're going to get back to the ANOVA table in a little while, but remember, from our simple linear regression, we'll review it again in just a minute, when we're talking about the ANOVA table, two of the variables in the table were the MSR, mean square regression, and mean square error. Also, remember, to calculate the mean square regression, we took the regression sum of squares and divided it by its degrees of freedom, k. That's how we calculated MSR. To calculate MSE, we took the sum of squared error, and we divided it by its degrees of freedom, which is n minus k minus 1. Okay, we could have talked about that in the previous reading as n minus 2, but it's the same thing, n minus k minus 1. Okay, so we know the degrees of freedom in the numerator. Okay, that's k. We know the degrees of freedom in the denominator. That's n minus k minus 1. We calculate this. We look up the critical F value, and then we are going to perform our test. So when we look up the critical F value, what we're going to see is we're going to say, well, how many degrees of freedom do we have in the numerator? That's just going to be equal to k, the number of independent variables. And then we're going to say how many in the denominator. That's going to be n minus k minus 1, which in our case is 89. So if we come in here, we look at 3 degrees of freedom in the numerator, 89 in the denominator, what we get is 2.7. So this is what the F table would look like. Okay, we get a 2.7 as the critical F. Okay, if we go in and actually test this, okay, so again, borrowing some data from the table, we'll come back and look at this again in a moment. So we're going to get an MSR of 759.2 and MSE, mean square error, of 3.6. Those are both come out of the ANOVA table. We are going to review it, so if you felt a little fishy with it or a little uncertain with it when we were doing a simple linear regression, we're going to go back over in just a minute. Okay, but what we get is a calculated F, or an F statistic of 210. We're going to compare that to our F of 2.7. So we're looking at our asymmetric distribution here. So we were looking for something that was going to be greater than 2.7. Well, we come with something way out here. This 210. It's way gone from 2.7. So we're going to reject the idea that all the coefficients are simultaneously equal to 0. Should I be surprised by this great big F statistic? Well, no. Remember, when I tested the coefficients individually, 2 of them were individually significant with a p-value less than 0.001. That is, they would be significant beyond the 99.9% level. So what would be the probability now that I test the model, okay, that while they individually look so significant, now they're actually equal to 0. Okay, well, the model, of course, is going to end up significant when you have 2 highly significant variables, or very frequently it's going to be significant anyway. So in this case, we would say that it appears that the model is significant as a whole. Of course, if one of the variables ends up being significant, it's very likely that you're going to be able to reject the null on the F stat. All right, I'm erasing some of my chicken scratch here, so we're going to reject HO and conclude that at least one of the slope coefficients is different than 0. Now, we talked about R squared when we were doing simple linear regression. We said the R squared was the percent of the variation in the dependent variable that was explained by the independent variable. So in this case, if we went to our ANOVA table, what we would see is that we have an R squared for this equation of 87.6. Remember how we calculated that. Okay, we calculated it as regression sum of squares over sum of squares total. So that was the total, what was explained over the total variability. That equals 87.6%. So in this case, these researchers were successful in explaining 87.6% of the variation in hedge funds based on the variation in the Wilshire Index, the High Yield Bond Index, and the Emerging Market Index. Now, that's the R squared, and its interpretation is exactly like what we would have seen in simple linear regression. And now there is a follow-on concept here when we're talking about multiple regression. And the notion is this. If we think about r squared, I think I can call up a picture here. If we think about r squared, as we increase k, okay, that is in the horizontal dimension here, what happens to r squared? Well, r squared is going to increase as we increase k. Maybe a better way of saying that is it can't decrease as we increase k. So if we had three explanatory variables in our model, if we went to 4, the new variable can't destroy the explanatory power of the old variables, all right? So as you add variables to your model, your r squared can either, I guess at some point, stay the same, but think of it as increasing and probably increasing at a decreasing rate. The trouble with that is as you, and at first glance you say, hey, well, let's just keep throwing new variables into the model, and that's going to increase our explanatory power. Well, the problem with that is, as you add new variables to the model, there are costs associated with that. One, of course, is just the cost of obtaining the data, but also there's some econometric costs in the fact that we can start to introduce multicollinearity and some other things like that. So there's cost associated with it. So what the adjusted r squared does is it compares the change in r squared essentially to the cost of the addition of another variable. So we're going to get this adjusted r squared, and what we'll see is that the adjusted r squared is going to increase as we add k, that is, add explanatory variables up to some point, but then adjusted r squared is actually going to start falling, and what that is indicating is that the marginal explanatory power of those new variables is the benefit is less than the cost. So while I'm not sure this is the actual interpretation in the real world among researchers, you can think of this, okay, when you come to the top of this adjusted r squared curve, that's going to be your maximum adjusted r squared, and that's going to give us the optimal number of independent variables. Now, in truth, we may want to be over here. We may want to be past that because there's some variable that we really want to understand how it's related to, say, stock returns or hedge fund returns. But I think as an interpretation, once you get to where the adjusted r squared starts to fall, you have to be really careful about adding more variables to your model. So looking at a quick example here, suppose we took our hedge fund example where we had 3 independent variables and we added 15 more. So we went from 3 to 18. Okay, well, the original r squared was 87.6. If you add 15 more variables, the only way r squared can move is up, so it moves to 89%. So you pick up a little bit of explanatory power, but the adjusted r squared, when you had 3 variables in the model, was 87.2. What's happening to the adjusted r squared with the addition of 15 variables? The adjusted r squared is actually starting to fall. So we see that we're in this realm where adjusted r squared is starting to fall. So if you have a choice between these two models, which seems a little artificial, we added 15 variables all at once, but nonetheless, okay, which one of these would you choose? You would choose the first model. Why? The adjusted r squared is higher and the model is more parsimonious. That means, it is simple. It does more with less type thing. So anyway, so the more parsimonious model here is the one with the higher r squared, the one with the higher adjusted r squared. That is the 87.2. If you add all those variables, there's some increase in gross explanatory power, but it just doesn't justify the cost of the addition of 15 variables. All right, so I promised you we'd get back to the ANOVA tables here. So our ANOVA table, looking at this, we're saying, okay, we've got the same thing we've seen previously. So our degrees of freedom for the for regression sum of squares is k. For the sum of squared errors is n minus k minus 1. Remember, this sums vertically. This first column sums vertically. So you take k plus n minus k minus 1. It's going to equal to n minus 1. Likewise, this second column sums vertically. So if you take RSS, that's what's explained. SSE, that's what's not explained. That has to equal the total of what was to be explained. And then we work this way to get the mean squares. So if you take the RSS divided by k, you get the mean square regression. If you take SSE divided by n minus k minus 1, you get the MSE, or mean square error. Okay, and that is the completion of your table. All right. Now what you need to be able to do is take one of these tables with some holes in it, okay, and then fill in the holes. So be able to sum or do whatever's required, like a game, like a Rubik's Cube, and then be able to calculate 3 variables, the r squared, the SEE, and compute an f-test if they were to ask you to do that. So looking at our data, when we look at the hedge fund returns, the regression sum of squares is 2277. The total sum of squares is 2600. Okay, so we explained 2200 out of 2600. That's where we got the r squared. Okay, we want to construct the ANOVA table, calculate the R squared, calculate the SEE. We've already calculated the F statistic. You'll need to remember that N is 93 and K is equal to 3. So here we can fill in the table. So we know that the degrees of freedom associated with the regression sum of squares is 3. So we take 2277 divided by 3. That's where we got the 79.2 that we used in the numerator of the F statistic that we calculated 5 or 6 slides ago. Okay, so we can come down to the next line. Okay, so we know that this is going to be, this is N minus K minus 1. Okay, that's 93 minus 3 minus 1, so 89. How did we get this 322? Well, we knew that 2277.6 plus whatever the sum of squared errors was has got to equal 2600, so we had to back into this number, right? But it turns out to be 322, so we take 322.4, divide it by its degrees of freedom, that gives us 3.6. Remember that that was the denominator in our F statistic that we used 4 or 5 slides ago. Well, if you take 93, if you take 3 plus 89, you're going to end up with 92. That's N minus 1. Okay? And if you take regression sum of squares divided by the total, what was explained over the total to be explained, that's where we got the 87.6. And then if you take the square root of MSE, okay, that is square root of 3.6, you get the SEE. Remember, both the R square and the adjusted R square are measures of goodness of fit. What you would like to see is high R square, which implies low SEE. We talked about the relationship between those two in the last reading. There were some nice pictures on how that those two things interacted. All right, so what about dummy variables here? So dummy variables, this is going to finish up part 1. We still have part 2 to get through on this, but nonetheless, dummy variables, this is where we're using a 0 or a 1, also called a binary variable. So we have a dummy variable as an independent variable. So it's important to recognize that what we're talking about here is using a binary variable as an independent variable, something for the time of the year, or whether the firm was in bankruptcy when these returns were earned, or something that's going to be either on or off. Well, we can regress EPS, that is earnings per share, against binary variables that proxy for quarter. So if you want to know how EPS changes for each quarter, well, we can put in some binary variables or some dummy variables for the quarter that the earnings observation comes from. So the dummy variable trap, a couple of things you need to know here. One is the dummy variable trap, but then you need to know how to interpret the dummy variables. If you got that, then I think you know just about everything you need to know about dummy variables. Anyway, the dummy variable trap is you always use one less dummy variable than there are states of the world. So if there's 2 states of the world, bankruptcy, filed for bankruptcy, haven't filed for bankruptcy, that's 2 states of the world, you only need one dummy variable. So you'll turn it on if they're in bankruptcy, and it'll be 0 otherwise. Okay, the one that you're not proxying is called the suppressed variable. So if you have 4 quarters in a year, you're going to use 3 dummy variables. A dummy variable for the first quarter, second quarter, and third quarter. So what you're effectively doing is you're comparing the first quarter to the fourth quarter, or the second quarter to the fourth quarter, or the third quarter to the fourth quarter, but one of the variables has to be suppressed, otherwise you end up with fairly massive multicollinearity problems, all right? So anyway, so here we're going to regress EPS, so we have a